So working through Unit 6 and 10, Lesson B, multiple choice. Don't ask me why question 11's in there. We can't do it yet. It's a Unit 7 question, so we're just going to skip it. Bam. All right. Guitar string of length L can vibrate with with three antinodes as shown above. The straight dashed line shows the equilibrium position of the string. The wave pattern is most likely formed by the superposition of which of the following pulses or waves? So we know that it's a standing wave is formed when it gets reflected back on itself. So let's see here. We have A shows a wave front coming in and the reverse coming back at it. Not sure how two waves leaving each other work. That's a little odd for B. Two periodic waves of wavelength L over 3, one moving to the left and another moving to the right. Left and right. Two periodic waves of wavelength 2L over 3. That makes more sense because I got 3 halves of a wave there. So the 2 over 3 makes a heck of a lot more sense. So it should be two identical waves overlapping each other. One coming in like this. It has 3 sections, right? Up, down, up, yep. And the other one coming at it like this. It's reflection. They're coming at each other, but they're both going to be 3 halves, right? The length of this is going to be 3 over 2 wavelengths, so it's going to make it the length of a wavelength is 2/3 of it. So let's go with D. Kind of a weird question. One end of a horizontal string is fixed to a wall. A transverse wave pulse generated at the other end moves towards the wall as shown. It's reflected off the wall. Properties of the reflected pulse. There's a similar question in the previous one, where in this case it's going to reflect back when it leaves the wall, coming off the wall. It'll be upside down. So it'll be on the opposite side of the string. We know that. It will not have a greater amplitude. That would require an input of energy. It would violate the conservation of energy. And it can't have a greater speed because it's the same string, and presumably they haven't changed the speed in the string by making it more tense. So 3 only. Figure above shows a portion of a periodic wave on a string at a particular moment in time. The vertical arrows indicate the direction of the velocity of some of the points on the string. Is the wave moving to the left or to the right? All right, this is a tricky question. So this is on the way up, while this is on the way down. That means in a little bit, this crest will be here. So I'm going to say to the left because this is a future crest. As it goes up, this and this will be going down, and the crest will show up here now. So I'm going to say to the left. But that's a tricky little question. Radio speaker produces a sound when a membrane called a diaphragm vibrates as shown above. A person turns up the volume on the radio. Which of the following aspects of the motion of a point of the diaphragm must increase? So when this thing moves back and forth, that's what produces the sound. When you turn up the volume, that makes the amplitude. So instead of vibrating back and forth this far, it might vibrate back and forth farther. Okay, maybe that's a bit of an exaggeration, but you get the idea. So the maximum displacement will definitely increase. But I'm not sure that's the only thing, because in order to get from here and back again and here to here to get that to cover that bigger distance, I would think the average speed would have to be higher as well for a particle, not the speed of the wave, but for a piece of the diaphragm would have to move faster in order to cover that bigger distance in the same amount of time. So I would say both the maximum displacement and the average speed for this one. Let's see, which question is this? This is number 15. All right, and I would be correct, so that's good. I just want to verify with the answers to make sure I'm not leading you astray. Figure above shows a block on a horizontal surface attached to the top view, top to two springs, so it's going to oscillate back and forth this way. A light string is attached to one side of the block and initially lies in a straight line across the surface. The other end of the string is free to move. There is significant friction between the block and the surface, but negligible friction between the string and the surface. The block is displaced a distance and released. So since there's friction, there's going to be something called damping. It's not going to change the distance between waves or anything like that, but the amplitude is going to get less with time. So initially, the wavelengths will be large. Now be careful. This is a tempting answer right here, but it's not right because this is the wave it made first right here. And it wouldn't make a small wave first, it would make a big one, and later would be making small waves because it would have lost some of its energy. This makes a lot more sense. This would have been the first wave it made. It would, while it still have a big amplitude, because of friction, it wouldn't move as. Notice the wavelengths are the same. That's no big deal, but the amplitude gets less and less. So C is the best answer there. This doesn't make sense because it doesn't show any loss of energy. And this has this weird, like it doesn't have much in the beginning, then has a lot in the middle. This is just bizarre right here. 17. Two wave pulses, X and Y, shown above, are moving toward each other in the same medium. Which of the following patterns could result at some instant as the pulses pass through each other? It's a tricky one. This is a tricky one because A, there's multiple possibilities. But let's see. I don't see any way that these can cancel each other out completely. If these were inverted, like say this one was up here and this one was down here, then I could see how they would cancel. I don't see this being a possibility. I don't see how they're going to cancel each other out completely. Um, when just these sections overlap, I would expect something like this, where it would be way far down here. So one is a definite possibility. Um, and when they move past each other, when the two low parts are past each other, but the two high parts are overlapping, I would expect something like this. So I'm going to say 1 and 3. Is that an option? It says C. Let's see if I'm right. 17. Yeah, I'm right. What do you know? But yeah, I don't see any way in which they're going to cancel each other out. Frequencies of the first two overtones for the second and third harmonics of a vibrating string are F and 3F over 2. Fundamental frequency will be the difference between them. So it'll be 3F over 2 minus F. Or if you want to, 2 over 2F, that's just 1. So I have 1 over 2F, or F over 2. So if something vibrates at its fundamental frequency, if you remember, that might be, say, 8 hertz. The next, the first harmonic is going to be double, that's going to be 16 hertz. The next harmonic is going to be 24 hertz. Notice that the difference between these two is still 8 hertz. You're going to add that every time. So if you to get the fundamental, you just need to subtract any two that are next to each other, any two harmonics. Principle of superposition states that you add the amplitude. So Here we go. The displacement of a medium at a point where waves meet. It's all about where waves meet. That's what the law of the principle of superposition is about. Is the sum of the displacements or amplitudes of the individual waves at that point. So, E. To determine the speed of waves on a string, some students tie a long string of unknown length between a wave generator and a wall. They vary the frequency f of the generator to get a standing wave. They count the nodes n and measure the wavelength. Got it, okay. They repeat the experiment, creating standing waves of different frequencies. Which of the following is the best relationship to graph to determine the speed of the waves? So I know that speed equals frequency times wavelength, but I want to make a graph that gives me the speed. So I need that to be the slope. So let's see. They want f as a function of. So let's make f keep f here. So f times wavelength equals speed. Let's divide by the wavelength. So I get f equals 1 over wavelength times v. So if I treat, in fact, let's write it like this. F equals v times 1 over wavelength. This is like my slope. This is my y. This is my x, so to speak, right? Quotation marks. So if I plot f as a function of 1 over the wavelength, that would work. Then the slope of that would be my velocity. All right, two tuning forks. Greatest frequency of beats. So beat frequency is just the difference between the two. So whichever one has the biggest difference when we subtract them. So this has a difference of 2, this has a difference of 1, this has a difference of 5, this has 3, and this has 6. So I'm going to go with A for 21. Whichever one is the biggest difference. That's all beat frequency is between two, is just subtract the two frequencies. Figure above shows a pole with a spring around it and a 0.1 kilogram block with a hole in the middle and the top of a spring, so it goes up and down as the spring oscillates. A light horizontal string is attached to a block on the wall. When the block is oscillating at 5 hertz, a standing wave is formed. What additional measurement is needed to determine the speed of the string? Well, if I know that's 5 hertz, one thing I could do is I just need to figure out the wavelength. So for example, if I could measure the total length of the string, it's clearly got 2¼ waves, so I could find the wavelength that way. So I could do it with the distance between the block and the wall. If I knew that, and I know that I have 1¼ waves, my apologies, I have 1.25 waves, and I know this length, I could divide to get that. All right, and that's it.